Very good morning for all of you. So today we will discuss about the third unit, which is energy conversion and storage. So before getting into that actual topic, let's have some recap. If you go to the page number 22 of unit 1, so I have an plot for the IV curve. Okay, this goes like this: potential in volt and the current density J, and I have a solid line that is showing something like that, and there is a dotted line which goes like that. I have divided into three regions, region 1 and there is a region 2. Okay, this is a dotted line for the IV curve. These are just imaginary lines which I have drawn to divide this graph into three parts. And also yesterday we discussed about the Butler-Ulmer equation, which shows how current density is related to exchange current density multiplied by e power minus beta, e power alpha nf eta by RT. If n is 1, so this alpha f eta by RT. If n is more than 1, then we can plug in those values. Then e power minus 1 minus alpha and nf eta by RT. So this is your Butler-Ulmer equation. This shows how the current is related to our potential, okay, and which is actually the current is scaled by this J0 value, exchange current density, which is specific to given redox couple. And as you see this IV curve which is here, initially as we draw the current, for a small change in current there is a huge change in potential here, and this region is called activation region, activation controlled region. Why this is called activation controlled region? You remember, any electrode you dip in a solution, it's going to form an electric double layer. This is a double layer. Okay, so in this electric double layer you have the solvent molecule attached to the metal electrode and also specifically absorbed anions or cations in there. And suppose you want to reduce a cation, say for example copper 2+, which is exist in the solution with its hydration sphere, because every cation or anion in the solution will have its hydration sphere or solvation sphere, depending upon if it is a water it's hydration sphere, if it is some other solvent it is a solvation sphere. Now if this copper, if I have to reduce this cupric ion, it has to go through this double electric double layer and then reach the electrode. Okay, when it goes through this electric double layer, it may be cutting down its hydration cell. It may be, suppose if copper 2+ associated with the 3 water molecules, that means copper 2+ surrounded by 3 water molecules, then if it has to go through this double layer, it may have to cut down some of its ligands, or it has to redesign its hydration cell and then it has to insert itself through the double layer and go there. So when you have to cut down these ligands around this, then it has to do some work. Okay, work means you have to spend some energy. So this ion will do that, taking energy from the available energy from the battery. That means the voltage of the battery will drop, because that much of voltage, this is the drop in voltage when no current flowing, this much voltage is drop is because that is taken for removing this or redoing this or redesigning their hydration cell so that it can reach the electrode surface. So it's called activation controlled region. And then you have mixed control region. Mixed region. What is mixed control region? As I told you, if we have to do a reaction, suppose let me take a copper electrode dipped in a copper sulfate solution, and if you want to reduce it, so you pump electron into this electrode. Okay, there will be a suitable counter electrode, let us not worry about that, this is our working electrode. Then the copper has to diffuse to the electrode surface from the bulk of the solution. As I told you before, this diffusion has certain speed. Ion cannot arbitrarily diffuse at any speed. It defined by the environment in which it is there, what is the Coulombic interaction this ion has with other ions in the solution, and what is the viscosity of the solution, what is the temperature, all that decides what is the diffusion coefficient of this ion in this particular situation. So depending upon that, there is a maximum current which can be defined as limiting current JL as NF, D and C by delta. This delta is the diffusion layer thickness, not double layer. This is a diffusion layer. Diffusion layer is a layer in which there is a concentration gradient of the species exists, right? So this is a maximum current you can draw. But this diffusion, because the diffusion layer start growing when you apply over potential, so to all other over potential except at the equilibrium potential where there is no reaction. Other than that, in any other potential if you go, there will be a growth of diffusion layer. Because of that, there will be a current which is controlled by the diffusion. So due to that reason, if you see, if there is no diffusion in the system, if the species are coming at the highest speed that is possible, that means the diffusion of the species in the system is not limiting my system, then I would have an IV curve which is something like this, which is defined by the Butler-Ulmer equation, because Butler-Ulmer equation, as I told you, assumes the concentration as a bulk concentration. Okay, that means the concentration on the electrode surface is not changing with the over potential. That is the assumption Butler-Ulmer equation makes. So then there is no question of mass transport there, because whatever may be the over potential, I assume same concentration in the electrode surface, just like in the bulk. But in the reality, the surface concentration of the electrode will decrease because you are consuming that reactant on the electrode surface, then it has to come from the bulk. So it causes a growth of a diffusion layer, thereby the current will be limited. Let's see, look at here, at this potential if I take, the current in the second curve is smaller compared to the first curve. So here it is more, here it is less. This is limited, so much is limited because of the diffusion issues. So the diffusion issues grows as you increase the over potential, because this is over potential direction, over potential increase this way. Okay, this is applied potential, this is over potential. So as the over potential increase, more and more diffusion issues will appear. At one point, the diffusion totally controls your system. That means whatever may be the potential, your current doesn't change. That means potential doesn't have any influence on the current now. So this region is not predicted by Butler-Ulmer equation, but it comes because the system has the real system has a limitation in terms of diffusion of the species. So this current is due to diffusion limited current. And then subsequently we have used Nernst equation to understand the Urbaic's diagram, Evans diagram with respect to corrosion, right? And now today we will use the Nernst equation to understand the voltage of the battery and what is the charging, discharging means, how do you characterize a battery, and what are the classifications in the batteries and things so on. Okay. So today's topic is energy conversion and storage. Conversion and storage. So I have started with the batteries. The batteries got two classification. One is primary battery, the other one is secondary battery or rechargeable batteries. These are the two types of batteries. So what is a primary battery? Primary battery means it's a single use battery. That means that it is a galvanic cell, because it's going to give power to you, just like our dry cell or Leclanche cell or alkaline cell, the Duracell that we use is all primary batteries, because in this battery once the reactants react, produce energy, then you cannot recharge them, you cannot bring back to the original state. For example, in this case, let me have an example and explain you. Zinc MnO2 alkaline battery. This is the regular Duracell battery. It's an alkaline battery, so its voltage is roughly about 1.5 volt. Why is it giving 1.5 volt? We will see in a minute. In zinc alkaline battery, the reactions are zinc ON2 reacts with OH minus ion, because it's alkaline battery, and produces zinc oxide plus 2 electron. So the way I have written is an oxidation reaction. The standard reduction potential of this reaction is minus 1.28 volt roughly versus SHE, standard hydrogen electrode. Similarly, the MnO2, which is the cathode material, will undergo produce Mn2O3 plus 2OH minus aqueous. This voltage, this I have written in the reduction form. So standard reduction potential of this was 1.18 volt or 15 volt versus SHE. Okay. So if you look at it, my zinc act as a anode because it has the most negative reduction potential. So when you compare the potentials of two different redox couple, what is the redox couple here? Zinc oxide is a redox couple. What is the redox couple here? MnO2, Mn2O3 is a redox couple here. So when you compare two different redox couple, you should compare in the same scale. That means if you are comparing oxidation potential, you should compare with respect to oxidation potential. If you are comparing reduction, if you are comparing them, then you can compare the reduction potential to understand which is going to be my anode and which is going to be cathode. So now I am comparing the two reduction potentials or standard potentials, and between these two, this is the most negative. That means my zinc will oxidize because that will serve as anode. Then if you want to calculate the cell potential, it is going to be E cathode minus E anode, that is 0.15 minus of minus 1.28, it's about 1.38, 1.43 volt. So this is the voltage of the alkaline batteries, but this is single use. What it means, once it becomes zinc oxide, the other side once it becomes Mn2O3, because this is called discharge reaction. This is a discharge reaction because this gives us power. So once it undergo discharge into zinc oxide Mn2O3, you cannot charge the battery to bring it back zinc oxide into zinc and Mn2O3 into MnO2. It is not possible. Okay, so that is why it is called primary battery. It will only work once. Once the reactions are over, it will stop giving the energy to you. Okay, this is a primary battery. So this battery was very prevalent in 19th century, late 19th century. Around the 20th century, middle of 20th century, there were rechargeable batteries were started coming up. Okay, so for example, what is a rechargeable battery? Rechargeable battery is the one we can use more than once. Okay, that means you use it, once you discharge, you charge it again, and then again you can discharge, charge it again you can discharge. So you can go on, continue to do many cycles like that. So for example, the regular lead acid battery that we have in our motorcycle or car is an example for the rechargeable battery. What happens in rechargeable battery? For example, lead you take solid lead plus HSO4 minus, it gives lead sulfate, solid proton plus 2 electron. So reduction potential of this reaction is minus 0.356 volt. Okay, that means lead and then another electrode is lead oxide HSO4 minus 3H plus reduction potential of this electrode is 1.7 volt. Okay. So in the previous case, in case of alkaline battery, zinc electrode we can call it as an anode. Okay, and the other electrode MnO2 can be called as a cathode because in the zinc electrode oxidation happens, so it is anode. In the other electrode reduction happens, so Mn2O3 is a cathode, MnO2 is a cathode. But in this case, when I discharge, lead will become lead sulfate and lead oxide will also become lead sulfate. So when I discharge, this acts like my anode because this is undergoing oxidation, because lead is 0 state, this lead sulfate is in lead 2 plus state. Similarly, here lead is in 4 plus state and it goes to 2 plus, from 4 plus to 2 plus. So that means this is going to be my anode and this electrode going to be my cathode when I discharge. But as I told you, this is a secondary battery. That means I can charge it back to the original state. So if I charge it back, what happens? Lead 2 plus is becoming lead. That means from 2 plus to 0. Then this becomes my cathode when you charge. Okay, and lead 2 plus becomes here 4 plus again. Then during charging, it becomes my anode. So if you see what was anode during discharge has become cathode during charge. So what was cathode during discharge become anode during charge. So it's very difficult to identify which is my anode, which is my cathode. It depends on whether you are discharging or charging the cell. Hence there is a new terminology which is adapted, which is called negative terminal and positive terminal. So what you need to do is you have to look at the discharge reaction. When you discharge, whichever the electrode where oxidation happens, okay, that's called negative terminal. That means lead is a negative terminal, where lead oxide is the positive terminal. Why is it? Because when the lead oxidizes, when the lead undergo oxidation in the sulfuric acid solution, this is my lead. When it undergo oxidation in sulfuric acid solution, this goes out as lead sulfate Pb2 plus. The 2 electron is left behind in the electrode. Now this electrode is having excess of electron, right? So that's why it's called negative terminal. Similarly, in the other side, electron will be consumed from the electrode, so it will be depleted in electron, right? That's called positive terminal. So we call under discharge condition whatever is anode is our negative terminal. Under same discharge condition, whatever was cathode is our positive terminal. So negative terminal and positive terminal are negative electrode and positive electrode are the terminologies used in the rechargeable batteries or secondary batteries, not the anode and cathodes. Okay. Now if you see the E cell value of the cell, E cathode, so among the two reduction potential, this is the most negative, then this will be my anode. So my cathode minus anode going to be about 2.0 something. So it's about a 2 volt battery. So lead acid battery is about a 2 volt battery. Okay. And what is there is another example which I can give you for the rechargeable batteries, that's called nickel cadmium battery. It's called nickel cadmium battery. So what are the reactions? Nickel oxyhydroxide. In nickel oxyhydroxide, nickel is in 3 plus state plus H2O plus electron gives nickel hydroxide plus OH minus. E naught value reduction potential is minus 0.86. That is with respect to standard hydrogen electrode. Similarly, cadmium plus 2 electron. Okay. The standard reduction potential of this is 0.49 volt versus SHG. Okay. So now what is the E cell? E cell going to be among these two, this is most negative reduction potential, that means that's going to be my anode. So my E cell is 0.49 minus of minus 0.86, roughly about 1.2 volt. Okay. So nickel cadmium battery about 1.3. So 1.3 volt. So nickel cadmium battery is an example for the rechargeable or secondary type battery, wherein during discharge the cadmium will undergo during discharge. So because this is most negative, right? So when it's most negative, that should act as an anode during discharge. So anode means it's when oxidation. So where is oxidation? This is going to be how much? So this is 2 plus, this 3 plus, then your U cell going to be 1.3 volt, where cadmium going to oxidize to cadmium hydroxide. I think the E naught values I have reversed. So this is supposed to be, my cathode during, because it's reduction, this should be about minus 0.6 and 0.4 volt roughly. So then your E cell going to be E anode. So E cathode, your E cathode is this nickel oxide acid going to nickel hydroxide, your E anode is cadmium going to cadmium hydroxide. So cathode minus anode, you are going to get about 1.3 volt. So during charging, the reverse will occur, right? So then there are so many batteries, then how do you qualify which battery that you want? The problem is the lead battery, lead is very abundant, so it is very cheap, so inexpensive battery. The atomic weight of lead is about 207 gram per mole, and if you look at the for zinc, it is about 65 gram per mole, and for lithium it's about 6 gram per mole. So if you make a battery out of lead, so 1 mole of lead going to lead 2 plus will give 2 moles of electron, correct? Similarly, 1 mole of zinc going to zinc 2 plus will give us also 2 moles of electron, because each zinc gives 2 electron. And if I take lithium going to lithium plus, so this gives 1 mole of lithium gives 1 mole of electron. But in terms of charge, if you see, if I have 2 moles of lithium, then it will give 2 moles of electron. So in terms of charge, all these reactions are giving same amount of charge, but this much of charge you are getting from 207 gram of lead, and the same amount of charge you are getting from the 65 gram of zinc, and 2 moles of charge you are getting from 12 grams of lithium, correct? So the amount of material that you require to get the same amount of charge is less in lithium, because lithium is lighter compared to zinc and lead. So what does it mean? If I calculate what is my energy density or charge density, it is going to be higher for the lithium battery compared to any other two, correct? So in that sense, if I suppose if I have to utilize a battery in my car to run the car, not just to power the car. So if I have to run the car in a battery, then I need to have a battery which is weightless and gives me as much as energy or power that I want. In that case, you should go for the lithium battery. Suppose you don't worry about the weight of the battery, that means for a stationary application, then you can go for the lead acid battery. But in addition to that, lead acid battery has some disadvantages, like lead acid battery has to be properly maintained. That means you should never allow the electrolyte to dry and never allow the cell to completely discharge. Okay. So these things you have to make sure, or you should not leave the battery in a charged mode for a longer time. For example, you charge a lead acid battery and leave it for 3 months and come back and try to discharge, it may not, because of some other issues in the charged state. The battery will automatically self discharge, and after self discharge it forms a non-conducting lead sulfate coating on the electrode surface that prevents battery from starting again. So there are issues with that. So if you properly maintain, that means the maintenance is high on lead acid battery. But there is no such issues when it comes for lithium battery. In lithium batteries, the self life is high and the self discharge is low, and in fact the voltage of the lithium battery, if you calculate, they are 2 to 3 times higher than the nickel cadmium battery, and at least 2 times higher than the lead acid batteries, things like that. So lithium battery, when I say lithium battery, so what's the reaction? So I may have something like this: lithium going to lithium plus electron. Okay, so this goes into the solution, SOL solution, and then if you use MnO2 as your cathode, then this is going to react with the lithium. It's going to produce MnOOLi. So magnesium, manganese 4 plus state becomes a 3 plus state, manganese oxy, lithiated manganese oxide. So then lithium gets oxidized here and MnO2 gets reduced here. So this is an example for a primary lithium battery. This is a primary lithium battery. Okay. So we can do the calculations. For example, there's another primary lithium battery. There's an example for it. It's a lithium thionyl chloride battery. So that is, lithium will undergo oxidation and SOCl2 is the cathode here, and that will take the electron released by the lithium, undergo reduction, SO2, sulfur and 4Cl minus. So the total reaction will be, we add them these two, then it is going to be 4 lithium giving rise to, because you need 4 electron here, that means this you need to multiply by 4, right? Then SO2 plus sulfur plus 4 lithium chloride. So this is a net reaction. The voltage of this cell is 3.65 volt. This is about 1.6 volt higher than the lead acid battery. Okay, and theoretical energy density is about 48 into 10 power 3 watt hour per kg. I will come to this how to calculate the theoretical energy density with the battery, and the practical energy, this is theoretical energy density. Practical energy density is about 700 watt hour per kg. Okay. So the lithium primary battery, lithium thionyl chloride, gives the practical battery gives about 700 watt hour per kg with a voltage as high as 3.65 volts. Let us do the same calculation for a nickel cadmium battery, for example. For nickel cadmium battery, the net reaction is nickel oxyhydroxide reacts with cadmium plus 2H2O gives during discharge. This is during charge. It gives 2 times of NiOH2 plus cadmium hydroxide. This reaction has got a potential of about 1.29 volt. Okay. So what is the energy that is given out by battery? So when I calculate energy, I don't consider for measuring the weight of the battery, I don't consider the casing's weight or the electrolyte weight in the battery. I only consider the active material weight. That means this is the active material, because this is the one which is going to give me the energy. So I only consider the weight of this and this. Okay. So if I consider the active material, so if I run this battery, what is the energy I get? Delta G is NFE. Okay, E is a voltage, you multiply by charge, it becomes energy. So that's going to be roughly 2 times, because this is a 2 electron process, 96,485 into 1.29 is the voltage of the battery. That's roughly about 2.5 into 10 power 5 watt second, which is 69 watt hour. This is 69 watt hour. So much of energy you will get. Okay, watt is joules per second. So hour is also a unit of time. So this should be a fundamental unit of joules. So much of energy that you get from this battery. Now I calculate the weight of the total weight of the reactants. Okay. So sum of the molecular weight of this reactant going to be about 331.8. Okay. That means I take this 69, I divide by this 331.8 gram, then I get about it's about 208 watt hour per kg. Here in grams, here I have it in kilograms. 208 watt hour per kilogram of active material. That's a theoretical, because this value is a theoretical value and this is the weight of only the active materials, and from there I calculated this value. But practically, the practical energy density, this is called energy density because I normalize it with respect to the weight of the material, right. So this is about 40 watt hour per kg. Now you compare this value, we got about 40 watt hour per kg of practical energy density with a nickel cadmium rechargeable battery with the value of about 700 watt hour per kg that you get with a lithium thionyl chloride primary battery. So this is about some about roughly about 18 times is bigger than what nickel cadmium battery gives. So in that respect, these batteries are very interesting because they have a very high energy density compared to nickel cadmium. In case of lead, it will be even more less because of a heaviness of the lead, the element lead and lead sulfate, right. So now how do I define the quality of the battery? The quality of the battery will be defined using this watt hour per kg. This is the energy density, and then watt per kg. This is the how fast energy can be delivered, right. Watt is joules per second. So higher the water means more energy per second that you deliver. So what is the rate at which energy can be delivered comes from this quantity watt per kg. So if you know about watt hour per kg of a battery and watts per kg of the battery, then you have you can compare different batteries and make a informed judgment on which battery to select for the given application. Okay. But in case of primary battery, what we are worried about? In case of primary batteries, we are worried about their shelf life. What is shelf life? Because just like the alkaline battery where I use zinc as one electrode, other is MnO2. So if you look at the primary battery, if you ever break open these AA batteries or AAA batteries that you have got, okay, so you break them and you would see in the middle there is a carbon rod, okay, and then you have a tin which is made of zinc, and this is carbon rod, and the MnO2 in alkaline medium will be kept inside as a gel, okay. Now during the reaction the zinc will oxidize, okay, it will give electron and that electron will go to the carbon, there this MnO2 will be attracted and it will be reduced to Mn2O3. So this is the kind of a schematic that you would see, I mean arrangement that you would see if you cut open this commercial zinc alkaline batteries, right. But what is the problem here? The problem here is, what if this MnO2 reacts directly with the zinc, okay, it reacts with the zinc, then what will happen, if it directly reacts with the zinc, zinc will oxidize and MnO2 will be reduced, right, it will become zinc oxide, then Mn2O3. I have not balanced that equation, but this is a chemical reaction because the electron is directly transferred from zinc to MnO2. If this happens, the amount of MnO2 and zinc available in the battery will decrease with the time, and this is called a self-discharge. That means without giving an electrical output, the battery is undergoing a discharge, it is called a self-discharge. The self-discharge has to be minimum, then only you can store the battery for a longer time. Suppose you make a primary battery, it comes to the market, then the user takes it and puts it in his tape recorder or in wherever he wants that battery. So probably we would expect like 1 or 2 years of self life. If it is, the reactions between zinc and the MnO2 is so fast, the self discharge occurs very quickly that within a month of manufacturing, if the battery expires, it is not going to be useful for us. So we need to extend the expiry date of the battery as much as possible. For that, self discharge of the battery has to be minimum. So this is the biggest concern in a primary battery. The primary batteries are known to have a high self discharge, but self discharge is not an issue when it comes to for a rechargeable battery, because in case of rechargeable batteries or secondary batteries, even if there is a self discharge, okay, whether it is self discharge or the electrochemical discharge, the products are the same, right. It is going to be zinc oxide Mn2O3. Imagine for a second I can recharge this battery, but this is a primary battery, I cannot. But if I can recharge this battery, then I will apply energy to this battery, that means I will charge this battery, then I can reverse zinc oxide to zinc, Mn2O3 to MnO2, right. That means in case of rechargeable batteries, even if there is a self discharge, I can bring back those products to the original reactant state just by charging, and then I can use the battery again. So what does it mean? In case of primary batteries, there is a strict tolerance factor on the amount of self discharge one can take, but in case of rechargeable batteries, we are liberal, it can have a little higher self discharge than the primary batteries, simply because when you charge again, that is going to, even the self discharge product will go into the reactant again. So that is not an issue. So electrochemically we can revive the battery in case of a rechargeable battery. Am I right? So now what we have seen so far is we have considered only E0 values, and we have said that if the E0 is among the two redox couple, whichever has a negative E0 is the anode, whichever has the positive E0 is the cathode. But looking at this is purely a thermodynamic information, correct. And also we have calculated the energy density, that is using this formula delta G is equal to minus NFE, where I have used E in place of E, the voltage calculated for this combination of redox couples, and then F and N, and then calculated the energy available from such a battery. But again, this is a thermodynamic quantity, am I right? So this information, energy density or this voltage values, does not tell anything about the kinetics of the battery. What I mean by kinetics, for example, if I have say a reaction between hydrogen and oxygen that goes to say water, This is a fuel cell reaction. This fuel cell reaction delta G value is negative. That means it is a spontaneous process. But practically you take hydrogen gas and mix it with the oxygen gas, or you open the hydrogen cylinder, let it go into the air, you do not see water formation, right? Water does not form so easily. So what does it mean? Even though thermodynamics is allowing formation of water and it considers this reaction to be spontaneous, but the reaction rate is not appreciably high. That means we are not able to see the formation of water because water is forming at a very slow rate. So there is something to do with the kinetics of this reaction. So what is kinetics? As we discussed in the last class, we have an potential energy diagram where the reactions stay here, products stay here. If I have a situation like this according to thermodynamics, delta G is negative for this process because reactant is at a higher energy state than product. This is a reaction coordinate, this is potential energy or Gibbs energy. So if you see this reactant is at higher energy level than product, that means when you convert reactant to product, it is having a you will get an energy output from this process. But it will not go by this way, the reaction has to follow this path. This path is this energy between the reactant to the peak of this mountain is called activation energy or delta G, not double dagger. So every reaction, okay, that we encounter has got a activation energy. So the process should have enough energy, it should take enough energy from outside so that it can surmount this barrier and go to the products. In case of hydrogen and oxygen, at normal temperature and pressure, it will not be able to cross this barrier. That means the reaction is kinetically limited. Kinetically limited means thermodynamically it is allowed, but it is not happening because at normal temperature and pressure, the amount of energy it gets from the environment is not sufficient to scale this barrier. That means activation energy is much higher for this process, hence you do not see formation of water at ordinary conditions. Whereas if you take the hydrogen and oxygen at very high temperature, say 1000-2000 degrees Celsius, you may see they may react together, because at that high temperature it may get enough energy from its surrounding so that it can scale this mountain, become a product water. Or one more way is there. What is the other way? It is use of catalyst. If we use a catalyst, the catalyst role is to reduce the barrier. So this is the new activation energy profile once you add the catalyst. Once you add the catalyst, the activation energy which was here has come down. That means this is a new activation energy. Because you reduce the activation energy, there is a possibility even at room temperature the hydrogen and oxygen can react and produce water. So this is exactly what happens in a fuel cells. The fuel cell is a kind of a primary battery in the sense that you do not electrochemically recharge the fuel cell, you only always discharge, and you get the electrical energy from the chemical energy stored in the hydrogen. When it reacts with oxygen, it gives the energy output. So now what is the catalyst that is used in hydrogen oxygen fuel cell? Is a platinum. So you take a platinum catalyst. So on the platinum surface, hydrogen can easily absorb and produces 2 proton plus 2 electrons. Similarly, in the other side also is a platinum catalyst where oxygen is easily absorbed and it produces, it takes the electron from this step, so and also the protons, then electrons coming from this reaction goes here, okay, then it produces water. That means the proton has to move from the anode to cathode of the fuel cell. So this is the direction of movement of proton in case of proton connecting membrane fuel cells. This is moving this way, it is because the proton is produced at the anode and it is consumed at the cathode and the electrons comes through the external circuit. So if I have a better catalyst than platinum, then I would expect my activation barrier is reduced further, then the reaction rate increases at a given. So you can do it chemically this way. In electrochemically you can also do it, there is one more way, that is applying a potential. So just we discussed yesterday, when you apply over potential, so that means I shift my reactant energy state such that it goes up, then applying a over potential of N, F, eta, then my new reactant profile may be something like this. Now the new activation energy is my new activation energy is taking from this reactant, and this is a new activation state. This is my new activation energy. The magnitude of this activation energy is much lesser compared to the activation energy that is here. So either by applying a over potential to a given catalyst, we can change the rate of the reaction, or changing the catalyst with a better catalyst, we can also change the rate of the reaction. So this is how we do it in a battery. So that means it is not only important that thermodynamically a process to be spontaneous, it should be sufficiently faster to realize the energy delivered by that couple of redox couples. Okay. Now let us look at the example of lithium ion batteries. Before getting into that, so as I discussed before, so what is the difference between the Carnot in the Carnot engine? So it's a PV work, the pressure at volume. So what do? You do an isothermal expansion, that means at constant temperature T1, and then you get an adiabatic expansion. In adiabatic expansion, temperature falls below T1, and then you do an isothermal compression. Okay, suppose it has gone to a temperature say T2 here, then this isothermally I am going to compress. Then again an adiabatic compression where the temperature going to go beyond T2. So this is the, so this shaded area is the work done by the system, because if you take the first half cycle, this is my first half cycle, so this is the total shaded area, that is a work done by the system. Okay, and if you look at only this the area under this bottom curve, that is, so that means this part, this is work done on the system. Okay, so this shaded area, the entire shaded area below the top curve is a work done by the system, and this is work done on the system. The difference is the area enclosed by this loop. This is the difference. That means I remove the other part. So this difference part is this. So this is actually the work done by the system. But when order to do that, the system moves between the two temperatures. Okay. So the efficiency is defined as highest temperature is, in this case highest temperature is T1, T2 by T1. Okay. So this is the efficiency that you would expect from the Carnot engine, that depends on the two extreme temperatures that is used in extracting the heat. Basically what happens when you maintain a temperature difference, more is the temperature difference, more will be the quantity of heat that you would get. Q stands for heat. Okay, if less is the temperature difference, less heat will flow through the through that temperature difference. So you need to have a source and a sink in order to do this work in a Carnot engine. That's why it is inefficient. But if you take a fuel cell, you can in principally extract the chemical energy that is stored in the fuel cell into electrical energy. Okay, chemical energy into electrical energy by a isothermal process. Okay, so delta G is equal to minus NFE. You don't see the temperature appearing here, right? So you can convert, you can obtain the energy, the electrical energy from the chemical energy directly. So this is the beauty of fuel cell. That's why it is highly efficient compared to the Carnot engine. Okay, and most of the process that is happening in our body, actually it goes by this principle. So that's why our body chooses to communicate using an electrical signal, because that is more efficient compared to the heat signal. So if you go through the heat signal, then the efficiency of the process will be very low. In other words, so whatever we eat is combined with the oxygen from air and through a process which is very similar to what I have mentioned here, and converted to energy which is required for our body. So this is the most efficient process that is known, and nature adopts that for working of our body. So by now we have understood the importance of the lithium battery. The lithium battery has got a voltage which is higher than the other primary batteries. Even the lithium primary battery, that is lithium thionyl chloride, has got a voltage of 3.65 volt, and the shelf life is also higher compared to other primary batteries. And the cyclability means how many cycles we can use without losing performance is also more with this. And energy density expressed in the units of watt hour per kg. Some places energy density will be expressed in the unit of watt hour per liter. Where it is used? Wherever the volume is a constraint, weight is not a constraint. For example, wristwatches. Wristwatches, you have a very tiny volume available for running this, to place the battery inside the watches. In that case, we will be worried about what is the volumetric energy density. This is called volumetric energy density, because there we are worried about volume than the weight of the battery. In some places, like in the car, electrical car, where you have currently you have that IC engine that is in the front of the car. So that is actually the volume that is available for fitting the electrical engine there. Also, the weight of the engine, it matters, because this car has to carry that weight as it moves along. So both volume and weight constraints has to be considered, okay, when you are using the battery for a electrical car purpose. At this point, so I will take your questions and then I will explain about the lithium secondary, that means lithium rechargeable batteries. A second, okay. So you can post your questions, so I can answer to your questions now. I start answering your questions. The dry cell, if we heat little, it's giving some charge. Why? That's a question from BEC. That's because in a dry cell you have, as I told you, you have a container which itself is anode, and then you have a cathode, which is a carbon rod, and you have MnO2 in the gel form. So when you have the active material in a gel form, the movement of the active material will be limited. That means the MnO2 which is in the corner will take longer time to diffuse than MnO2 which is next to this carbon electrode, right. So as the battery reaction happens, the concentration of the MnO2 will decrease in the system. Why? Because MnO2 is converted into Mn2O3. So concentration of MnO2 decreases, hence the amount of material, because the diffusion is nothing but d, the diffusion coefficient of MnO2, and the concentration gradient dC by dx. As the concentration of MnO2 in the system falls, this quantity decrease, okay, and then the flux will decrease. The flux means the movement, the amount of material reaching every second to the carbon electrode will decrease. So it will reach a state that it no longer, the diffusion rate no longer can support the current that your instrument requires from that battery. Under that condition, the battery will stop working. But if you leave it ideal for some time, or if you heat this battery little bit, then this movement will increase, because the diffusion coefficient of the species at higher temperature will be higher. Because of that, the amount of material or MnO2 which is going to reach the carbon electrode will increase. Basically, during the time of heating, or when you leave the battery ideally for some time after discharge, then there will be a reorganization of MnO2 inside the cell will happen, and more MnO2 will be available around the carbon electrode. That is what actually giving you the capacity that you would see, the capacity that you see after heating this battery. But actually the total amount of energy that a battery can give is limited by the amount of active materials. Active material means MnO2 or zinc, that is the active material. So if you have 1 mole of MnO2, then you will get the energy which is proportional to that 1 mole only. You will not get extra energy just by heating. That means battery will not get charged by heating. In case of primary battery, it is not charging, it is simply the movement of the species which is enhanced, thereby you are having more MnO2 around your electrode, which is giving you the discharge, okay. So which is most efficient, whether it is a lead acid battery or lithium battery? Lithium battery is the most efficient because I have calculated for you the energy density, practical energy density for a nickel cadmium battery. So that was about 40 watt hour per kg. If you calculate the same thing for lead acid battery, it will be like about 20 watt hour per kg. That is much lower compared to something like 250 to 700 watt hour per kg that you get from the lithium battery. So definitely per kg of your battery, the amount of charge that you get is very limited in lead acid battery because of the heaviness of the lead that you are using. Secondly, lead acid battery can give you about 2.0 volt per cell, but whereas lithium battery can vary anywhere from 3 to 6 volt. Okay, so very high voltage that you get. And then shelf life. Shelf life means how long you can store the battery in the shelf without having any self discharge. Self discharge is, I told you, self discharge is the reactants react directly and give a discharge product without having an electrical output. So we have to minimize self discharge in order to maximize the shelf life. That means how long you can store the battery. That means extending the expiry date of the battery. So that is very good at lithium battery, and that is very poor for the lead acid battery. Considering the shelf life, the available voltage and available energy density and the rate capability, that means how much watt per kg can be delivered, how fast energy can be delivered. Considering the rate capability and all other parameters that I have listed, lithium battery is best compared to lead acid battery. However, since it has so much merits, the cost also so, that means lithium battery is many-fold costlier than the lead acid battery. So not for all application we can use lithium battery, only where it is really needed we can use like car, right. How energy barrier is minimized in hydrogen oxygen fuel cell? So as I explained to you, hydrogen plus oxygen giving water is a thermodynamically spontaneous process. That means delta G is negative. It doesn't mean that reaction will happen, because reaction is happening but at a very small rate that you cannot measure. In order to increase the rate at which this reaction happens, all we need to do is we have to reduce this activation barrier. And to product, so reaction coordinate gives free energy. So if you see, this activation barrier has to be reduced. If you have to reduce this activation barrier, you have to use a catalyst. If you use a catalyst, this activation barrier will be reduced because this reactant is absorbing on the catalyst surface. Absorbing, it has a conducive atmosphere or electrical property such that it can follow another route, okay, through which it can go to a product state. So basically we are changing the route that it follows to become a product. That is possible if you have this reactant absorbed on a catalyst surface, and that can do this magic. So that is how we reduce the activation energy barrier, thereby we are making the reaction happen which is otherwise not possible. And the same thing can be done by changing the over potential, because over potential also can change the energy state of the reactant, also the activation energy. So because of that we can change the rate of the reaction. When you change the rate of the reaction, you may able to see water forming in front of your eyes at very short time, that is possible. Under what condition does a cell phone battery burst? For a cell phone, if it is a lithium battery, there are several reasons, because I have discussed only the Nernst potentials or E0 values of the electrode and how do you make the battery and so on, but I have not told you about the reactions between the electrolyte and the electrode. Okay. In lithium battery, because lithium has a standard action potential of about minus 3.5 volt, which is, say, MnO2 may have some positive potential compared to lithium. So because of that, the lithium can react with your electrolyte. If the electrolyte if the electrolyte acts like an acceptor for the electron which is coming from the lithium. So if the electrolyte acts like an acceptor, then electrolyte will undergo some redox reaction as well as soon as it touches the lithium electrode. That is why we don't use water, because in water the decomposition potential of water is 1.23 volt. So which is positive to this, that means this can act as an anode and water can act as a cathode. So any electron that you get from the lithium oxidation will go into the water and it will electrolyze the water into oxygen and hydrogen, right. So this actually not oxygen, this will form H2 plus, because this will reduce the H plus in water to H2, then you have this formation of H2 plus OH minus. So this can happen because of the lithium in contact with the water. To prevent this, we need to use some electrolyte such that this reduction does not happen. So that is why non-aqueous electrolytes with lithium salt like lithium hexafluorophosphate are used as electrolyte in lithium batteries. But sometimes when you overcharge the battery, the charge, that extra charge that you are putting on the electrode may have a sufficient energy to react with the electrolyte. So that may lead to some gaseous products, that products may build up inside the closed lithium battery, and that may lead to bursting, or some kind of thermal runaway problems could be there. So the problems are many for lithium battery to burst. We cannot say one particular reason for it. So most of the reason is the reaction of electrolyte with the electrodes. So can we reduce the maintenance cost of the lead acid battery? Yes, maintenance cost of the lead acid battery is suppose if you build a battery management system, BMS, because most of the lithium battery that you get these days comes with a battery management system. Why? Because lithium battery itself is expensive component, and if you don't have a better battery management system, so you'll have a gas evolutions in lithium battery because of overcharging, which I just explained to you, or maybe some other thermal runaway problems that might cause the battery to fail. So in all the lithium batteries that you have comes with an inbuilt battery management system. Lead acid battery being very cheap, generally we don't have such a robust battery management system associated with lead acid battery. If we can make a BMS, surely BMS may be as costly as lead acid battery itself. So but this can help you maintain automatically the lead acid battery. That means it will not allow the lead acid battery to completely discharge, or it may not overcharge the battery, such as security checks can be included in the BMS, so that the cost of the battery and the BMS together will go up, but the life of the battery will be longer. So it is certainly possible. Only thing is one has to build a suitable BMS for it. Is it possible to construct a lead acid battery using sodium hydroxide solution? So all the battery works with the concept of the reversibility. That means in case of lead sulfate, which is one redox couple, the other redox couple is lead oxide, lead sulfate. These are all highly reversible redox couples, so that means you can convert lead into lead sulfate easily. Similarly, lead sulfate into lead, same is the case here. But in alkaline medium, probably you may have lead and lead hydroxide. This may not be a very good reversible type of redox couple. In that case, you may not be able to charge and discharge. So you may not be possible to do it in the alkaline medium. Why lithium battery is more useful than the nickel cadmium battery? Because as I told you, nickel cadmium battery is also an expensive compared to lead acid battery due to nickel and cadmium which are involved, and the voltage that you get is about 1.2 volt, but in case of lithium battery you get about 3 to 6 volt, and this is also expensive compared to lead acid battery, even compared to nickel cadmium battery. But the shelf life of lithium battery is very good, and cycle life or cyclability or rate capability, that means how fast or how slow that you can charge, the rate capability is also very good with the lithium batteries. Hence you can lithium batteries better than the nickel cadmium batteries. Moreover, the cadmium is associated with some environmental concerns and things like that. So why we need to maintain the specific gravity of sulfuric acid always 1.2 to 1.5? It is because as you see the lead acid battery reaction which I wrote, is here. If you see this, when you discharge the battery, lead consumes the sulfuric acid and forms the lead sulfate. For example, here 2H plus is taken, because H2SO4 has 2 H plus, that 1 H plus become 1 H plus, 1 H plus in the solution, this releases 2 H plus, and then here it forms water here taking that H plus, it consumes this H plus in the positive electrode, it consumes H plus, produces water. So in other words, when you discharge the battery, sulfuric acid is consumed and lead sulfate is produced along with water. What does it mean is the concentration of the acid decreases as you discharge the battery. When you charge the battery, sulfuric acid is returned again, right? When you go back this way, you get back the sulfuric acid. When you go back this way, you get the sulfuric acid back. That means when you discharge the battery, sulfuric acid concentration is going to decrease, and you charge the battery, it is going to increase. That means the conductivity of the electrolyte depends on the proton in the solution. So it is important to maintain excess of proton always in order to maintain the conductivity in the battery. So people have optimized specific gravity of about 1.5 to be suitable for lead acid battery. That is why it has been done. So what are the batteries used in the wristwatches and calculators? That is generally alkaline silver battery is used, or the nickel cadmium battery is also used. Sometimes zinc batteries are, mostly it is silver batteries. Silver batteries are used in the wristwatches. So what is the difference between the battery and battery cell? A cell means one electrode of this and one electrode of this. That means it's a single cell. You have one anode, one cathode dipped in an electrolyte, that is a cell. So if we put several cells, because I call it as a negative electrode. So this is negative electrode and PbO2 is a positive electrode. So I combine several negative and positive electrodes in a series, or I can combine them in a parallel mode. That means this is parallel mode. Okay. So then it becomes a battery, which is actually a stack of many cells together. This is a serial connection, this is a parallel connection. In serial connection you multiply the voltage, in parallel connection you multiply the current. So this is a battery. So if you take your bike battery, if it is a 12 volt battery, it means typically 6 lead acid battery cells are put together to achieve that 12 volt. So if it is a 48 volt battery, then you can 48 divided by 2 is roughly, because lead acid battery has a voltage of 2 volt. So 48 divided by 2 is about 24 cells. That means 24 cells are put in series. That is how you get the 48 volt lead acid battery. So can you differentiate lithium and lithium ion battery? Yes, we can do. So earlier in lithium battery, you had lithium as anode and say MnO2 as cathode, for example. Then what happens? Lithium oxidizes to lithium plus electron. This is during discharge. At the same time, MnO2 is taking that electron and produces Mn2O3. So this is the reaction that happens. So the ion which is moving from the anode to cathode was lithium. So lithium was moving between the anode to cathode. So and this is, but in the anode you had lithium, in the cathode you had Mn2O3. And later there is a problem with this cell. Suppose if I have to recharge this cell, then the lithium which has left the anode during discharge will come back to the anode during charge, right? So let us assume we have a very nice flat lithium foil that we took and we did this reaction during discharge. Then lithium dissolved and went into the solution. When you charge, the lithium comes back and deposits on the lithium electrode. But we expect a uniform deposition of the lithium on this electrode, but on the contrary, what happens is lithium grows like a dendrite, like a thorn on these electrodes. It does not uniformly coat the lithium surface. If it grows like dendrites like this, these dendrites may grow sufficiently longer and it can touch the counter electrode, that means cathode. If it touches, then it is called electrical shorting of the battery, then the battery will no longer work. So to avoid that, later people have understood there is something called lithiated graphite. That means you have the graphite, which is a layers of graphene at a distance of 3.5 Armstrong from each other, right? So this bunch of graphene layers together, we call it as a graphite. If we can mix this graphite with lithium, then lithium will get intercalated between the graphite, okay, between the graphite layers. So if you look at the stoichiometry between the lithium to carbon, this is going to be LiC6, that means for every carbon there will be one lithium. So lithium here does not exist in the metallic form, it exists in the ionic form, lithium plus and C6 minus. It means carbon underwent reduction, 6 carbons together took 1 electron and 1 lithium gave 1 electron, so it becomes Li plus C6 minus. So this is, but since carbon is an extended network, it does not dissolve, so it is a solid matrix in which lithium is intercalated. This is called lithiated graphite. In case of lithium anode, lithium is in a zero oxidation state, whereas in lithiated graphite, lithium is Li plus, it is no longer Li0, okay. The electron of the lithium is stored in this graphene layers of graphite. So this is not a lithium battery. If you use this in place of anode, for example, if you use this in place of anode and MnO2 say as cathode, then what would be the reaction? The reaction would be, so LiC6 will give Li plus electron. So this electron will be taken by MnO2. I am not balancing the reactions, you may do it, Mn2O3, right, plus OH minus ion, all that will come. So now if you see, the lithium in the anode exists as lithium ion, and then when it discharge, the electron actually comes from the C6 minus, not from the lithium. But lithium, when this electron leaves that lithiated graphite, lithium also leaves it, okay, and it gets into the solution, and then it reaches the cathode where this electron and lithium are consumed to produce Mn2O3. So this is called a lithium ion battery, because lithium in this electrode exists as lithium ion, not as lithium metal. Whereas if you use pure lithium, then it is called lithium battery, because where lithium exists as lithium 0. Is it possible to increase the voltage of lead acid battery by increasing the concentration of H2SO4? Yes. If you look at the lead acid battery reactions which I wrote, proton is taking part in the reaction. So in principle, the activity of the proton in the solution might have some influence on the potential, but it need not exactly obey the Nernst equation. There could be some dependence on proton in reality. So it is possible, but there may not be an appreciable increase or decrease in the voltage as you change the concentration. So how can we apply nanotechnology for the improvement of secondary cells? Yes, we can apply. Probably I take this question and I explain in my second part of the lecture, okay. So I will explain this last question. Can you explain the construction of fuel cell and let us know the different fuel cells? Yes, there are a variety of fuel cells: alkaline fuel cell, acidic fuel cell, molten carbonate fuel cell, molten carbonate fuel cell, and molten oxide fuel cells, okay. There are a variety of phosphoric acid fuel cells and direct methanol fuel cells. But in all the cases, the anode is the one which will have a fuel, like hydrogen can be a fuel or methanol can be a fuel. For example, if methanol is a fuel, what happens? The methanol in water will oxidize to 6 proton plus 6 electron plus carbon dioxide, okay. So this proton will go through the membrane from the anode to the cathode, where cathode oxygen is given. So oxygen and 4 proton plus 4 electron will produce water. So it is only if you change the fuel, only the reaction of the anode will change, the reaction of the cathode will remain same, okay. So now I will get into the second part of this lecture. So this lecture is on lithium ion battery. So by now you may be familiar what is lithium ion battery, because I said lithium battery means you are using lithium metal, lithium is in zero state. In lithium ion battery you have lithium in the ionized form, right. So like lithiated graphite. So if I take a lithiated graphite, for example, this reaction. So this is a standard reduction reaction of lithium with carbon. So and then let us consider this. This is the reaction during charging of a lithium battery. the lithium battery. So what happens during charging? The lithium from the LiMn2O4, okay, lithium manganese oxide has been, the lithium from that matrix is extracted, okay, and it becomes Mn2O4, and the lithium that comes from there gets into the electrolyte and it reaches the anode or negative electrode. There it combines with the 6 carbon electron, gets intercalated into the between the graphene layers of the graphite. So it forms LiC6. So this is a charging process. What happens during discharge? During discharge, the reverse happens. LiC6 will give lithium plus electron. This is a galvanic cell, right? If I combine LiC6 with Mn2O4, that is a galvanic cell, because this will donate lithium that will intercalate into the LiMn2O4 and form LiMn2O4. Okay. So what if you look at in detail what happens in LiMn2O4 when I add lithium, for example, the Li plus Mn2O4 plus electron, it gives LiMnO4. What's the difference? Here Mn, manganese, is in oxidation state of 4, right? So when this lithium comes out from the lithiated graphite, it comes along with one electron. So it takes that lithium and the electron, it produces LiMn. In that, one of the Mn will be in oxidation state of 3, other will be in 4. Why? Because there are two Mn here. One of the Mn has taken this electron and got reduced. At the same time, the lithium plus is intercalated into the matrix of Mn2O4. Thereby it produced LiMn2O4, but in the product Mn is in two different oxidation state. So this is the discharge reaction at the positive electrode of the lithium Mn2O4 battery. Okay. So now the point is both LiC6 and Mn2O4 are crystals, they are in solid state, okay, they are in solid state. Imagine if I have Mn2O4 crystals of this dimension and then Mn2O4 crystals of smaller dimension, then if I have to lithiate these big crystals of Mn2O4, the lithium can either enter through this surface or through this surface or through this or through this. So it has to diffuse through this particle and reach the Mn2O4 which is inside. Okay. So Mn2O4 which are outside easy to lithiate, okay, because they will straight away react with the lithium. But those Mn2O4 which are inside the crystal, to access this lithium, lithium has to diffuse through this matrix. That means we are talking about lithium diffusion in solid state. In liquid state itself, diffusion is a tough process. So in solid state, it is going even more tougher process. So because of this, you will have over voltage in the cell. See, now to avoid over voltage, what you can do is you can divide this particle mechanically into many pieces and make a nanomaterial. So if you make a nanomaterial of Mn2O4 and make an positive electrode out of that, then you can imagine there are so many surfaces available for the lithium to get in. That means a diffusion of lithium inside these nanoparticles of Mn2O4 will be very easier. So the reaction requires less penalty in terms of energy, so that over potential of the cell will be lower. So this is where you can make use of nanotechnology to design an electrode wherein the over potential due to lithium diffusion is reduced, so that over potential is available as an electrical energy for you. So this is how you can maximize the performance of the battery. Suppose I have iron phosphate as my, say, cathode material, or this is called cathode material, or positive electrode. And what happens? Then you have lithium plus electron coming from there, right? So you please note there are two typos in page number 8, that is equation 10 and equation 11, 8. So there should be an electron here, plus electron. Similarly, there should be an electron here, right? So then only you can reduce 4 plus to 3 plus, right? So lithium is in one oxidation state, Mn is in 3 and 4. So now if I take this as an example, then the lithium which come out from the LiC6 lithiated graphite along with the electron which is coming through the external circuit is now reaching the cathode material or positive electrode, and now iron is in oxidation state of 3 here. It will be converted to oxidation state of 2 now, because it will become lithium FePO4. Okay. So this is the discharge reaction. So when you charge, the lithium from this matrix will be stripped. As it is stripped, one iron also will be oxidized from the oxidation state of 2 to 3, and then it will come to your graphite electrode where lithium will be intercalated again. So this will be the charge discharge reactions of lithium iron phosphate cathode materials. Why the iron metal is interesting compared to the manganese, or there is one more metal called lithium cobalt oxide. Lithium cobalt oxide is the same thing, because this is going to be in oxidation state of 3 plus, this is in 1 plus, and together this is 4 minus, so this is electroneutral. So if I have to extract lithium from this, is going to go like this. That means you will have your cobalt going to 4 plus state when one lithium is removed. Okay. So this is the charge reaction of the cathode material LiCO2. But in practically, you may not be able to extract 1 lithium per LiCO2. Maybe the amount of lithium that you can extract may be limited, because if you extract all the lithium from the matrix, maybe the crystal structure of LiCO2 may collapse and it will undergo phase transformation, go to some other crystal system. In order to avoid, generally we will only extract 0.5 of lithium from this. That means if I have say LiCO2, I can extract only up to this point, 0.5 COO2, that is 0.5 lithium. That means every mole of LiCO2 will give only half a mole of lithium. If you try to extract during charging beyond this, this structure of this metal may collapse irreversibly. That means once it collapses, when you charge, it will not come back to this structure. It will be an irreversible transformation. Because of this practical limitation, even though each LiCO2 can give 1 lithium, but in practically you will be able to extract only 50% of the lithium. So that LiC6 has a potential. So here this is one particular example, the lithium secondary battery, where you may not be able to use standard hydrogen electrode as a reference electrode, because there is an aqueous system, and in lithium battery you are using a non-aqueous system. If the water gets into the lithium battery, as I told you, water electrolyzing potential is 1.23, which is much lower than the lithium's potential of minus 3.5 volt. So the water will be decomposed. So we are not allowed to use water in the system. So we may not able to use the standard hydrogen electrode or caramel electrode or silver chloride, because all of them aqueous system based. So here we will use a pseudo reference electrode, that is lithium itself. I use pure lithium as a pseudo reference electrode. So the potential of LiC6 versus lithium, which is a pseudo reference electrode, is about 0.2 volt. Okay. Similarly, for LiCO2, the potential of LiCO2 with respect to a pseudo reference electrode of lithium is about 4.0 volt. So now again you can compare between these two. This is the most negative among these two. That means my lithium C6 will be the anode, and among these two this is the most positive. That means LiCO2 will lithium extracted form of the LiCO2 will be the, what is the lithium extracted form? That is COO2 or Li1 minus X. Here this is going to be LiC6 Li plus. This is a redox couple for the anode, this is a redox couple for the cathode. So now the E cell going to be E cathode minus E anode, that is 4 minus 0.2 volt, which is 3.8 volt. So 3.8 volt is a typical voltage of lithiated graphite anode versus LiCO2 cathode. Okay. So during discharge, this should be the form, because it should be lean in lithium composition, then only you can intercalate the lithium. During charge, lithium will be taken from this and be deposited in the lithiated graphite. So this is going to be the reaction in the lithium battery. This battery gives typically about 620 watt-hour per liter of volumetric energy density and energy density of about 250 watt-hour per kg. You compare this against 40 watt-hour kg that you got with the nickel cadmium battery and about 20 watt-hour per kg that you got with the lithium battery. In any case, is much higher compared to those batteries. Also, the cost of these materials is also higher, and the cobalt is environmentally unfriendly. So, people are going away from the cobalt, they are trying to use iron, which is more abundant and friendly, environmental friendly. So, lithium iron phosphate is an interesting material. Again, just like in the case of cobalt oxide, lithium iron phosphate also, you may not be able to extract one lithium for lithium iron phosphate, you may be able to extract only a part of it, okay, and because you need to preserve the structure of the lithium, okay. So, hence you can structure of the lithium iron phosphate, hence only a part of lithium can be extracted from this system as well. So, most of the lithium battery cathode materials will have such a limitation in terms of lithium extraction from its structure. And now let us go to the last topic of this session, that is again it is on the primary battery of lithium or even if the secondary battery. Generally the batteries are designed such a way that when we dispose the battery, there should not be any fire hazard or a health hazard to this battery. For example, let me take the example of lithium thionyl chloride. So, in this case lithium goes to lithium plus electron and thionyl chloride is converted into SO2 plus S plus 4 chloride. So, 4 lithium, this is a net reaction is 4 lithium plus 2 thionyl chloride giving rise to SO2 plus sulfur plus 4 lithium chloride. So, what is the issue here? Suppose after using this battery, this is a primary battery. So, as I told you, not all the reactants will be completely used because of the diffusional issues. Just like in a zinc MnO2 battery, here also thionyl chloride will be kept in the gel form inside the battery. So, some amount of thionyl chloride will be unreacted. If the thionyl chloride is unreacted, then some amount of lithium also may be unreacted because they are kept in a certain ratio. So, now if suppose imagine a battery where as per this reaction I need 4 moles of lithium for 2 moles of thionyl chloride. If I keep 4 moles of lithium and 2 moles of thionyl chloride and make a battery, and suppose you have used about 1.7 moles of thionyl chloride during your discharge process and about 0.3 moles of SOCl2 is left, then there will be about 0.6 moles of lithium will be left in the system, correct, because stoichiometrically this is 2:1. So, if you have 0.3 moles of thionyl chloride left, then you will have a 0.6 moles of lithium left. If you dispose this battery and if someone cuts open it and lithium, because there is a lithium here, so it will come in contact with the air and moisture. As I told you, lithium will violently react with moisture because the reduction potential of water, oxygen redox couple or water hydrogen redox couple is much lower compared to the lithium potential. Similarly, lithium can directly also react with oxygen because lithium potential is minus 3.5 and oxygen to water redox couple is about 1.23 and water to H2 redox couple is about 0. So, in any case this will be the anode and this things will be a cathode. So, that means lithium can react with oxygen also, lithium can react with the water also. So, because of this process, lithium will violently react with the ambience and it may cause harm to the person who opened that cell. Hence, these kind of batteries are always made anode limited. That means, if I put 2 moles of this, I may have it only something like 3.4 moles of lithium. So, that means when you completely discharge this battery, in the battery there won't be any lithium left, there will be only thionyl chloride left. This is called anode limited architecture. That means I limit the amount of anode because this is the most dangerous substance and it causes health hazard compared to SOCl2. So, I design a battery such that stoichiometrically I keep less of lithium than thionyl chloride, so that after complete discharge of the battery, you may not have any lithium in 0 state, all the lithium would have gone to +1 state, which is harmless, so that even the battery is disposed, it won't cause any ill effect to the person who is handling that. So if we have other way, suppose we have stoichiometrically more lithium, then obviously at the end of the discharge of the battery, you will have a lithium left, which is going to cause the harm to our environments. So this is called limited structures. In some batteries, suppose let us take lead oxide, and another side is not lead oxide, this is redox couple is lead sulfate and lead oxide lead sulfate. Suppose between these two redox couples, if one of the redox couple is very slow in electrically, that means less reversible compared to the other one, generally we design a cell where this material compared to the material which is highly reversible, the irreversible material will be kept little more, okay, because of the poor reversibility of this material, we take more of that material so that the battery can maintain the capacity for sufficient number of cycles, okay. In this case, we increase the concentration of one particular material compared to the other, we are not following the stoichiometry, is because that material which we are keeping in excess probably not very reversible electrochemically, that is why we are having excess of that and making the battery. So now if I get back to the lithium battery, in lithium battery always the capacity of the lithium anode, for example LiC6 is about 350 milliampere hour per gram, okay. Milliampere hour per gram is going to be in the unit of coulombs per gram, correct. So if you take the lithium cobalt oxide, that is about 130 milliampere hour per gram, okay. So the capacity of this side, okay, for 1 gram of LiC6 you have about 350 milliampere hour, for the 1 gram of LiCO2 we have only 130 milliampere hour. All the commercially known cathode materials has got less capacity, this is called capacity because this comes out in the fundamental unit of capacitance, right. So this is a cathode material, in all the known cathode materials, most of them commercially has got a capacity, okay, which is lower than that of the anode materials. So that means we want to make a battery with 1 gram of this and 1 gram of LiCO2, then we should match the capacity of these two electrodes. That means I will have for 1 gram of LiC6, I will have more than 3 grams of LiCO2, right. Imagine if I find a material in place of LiCO2 that also has a capacity of 350 milliampere hour per gram, then instead of 3 gram, I may require only 1 gram of that material. What is the advantage of this? The advantage of this is the weight of the battery for a given capacity is reduced by 2 grams. That means it has a direct implication when you make a stack, because there are going to be several batteries, so it is going to add up to several kilograms. So if you are going to use it in an electrical car, this really matters because electrical car has a constraint both in the form of volumetric energy density and also gravimetric energy density. So finding a cathode material which has a higher capacity as equivalent to this anode material would be the area of research. It is actually the area of research right now. So we are trying to find more of cathode materials whose capacity can be enhanced such that with a lower amount of that material we are having a capacity very similar to the anode materials. So I will stop at this point. So I may take your questions for another 10 minutes now. So you may shoot your questions now. So ionization potential of lithium is too low. Is it help for efficiency of lithium in its battery? See, the material where it can be easily ionized is called highly electropositive. That means they are a donor. They can easily give the electron. That's why lithium in the electrochemical series, if you see, lithium has got a standard reduction potential of about minus 3.5 volt versus SHG. Whereas if you take hydrogen, hydrogen has got a potential of 0 volt versus SHG. That means compared to hydrogen, lithium is highly electropositive. They can easily give out the electron. That's why we are using them as a anode material in our lithium battery. Yes, does temperature will affect the efficiency of any battery? Yes, temperature will affect because temperature is a state function. So it's going to alter the state of the material. Okay, so it will. In addition to that, temperature also changes the mobility of lithium in the electrolyte because you have the lithium anode and you have a cathode LiCO2. So when you discharge, lithium moves from the anode to cathode. That means you need to have a lithium lean matrix here. So it will move from the anode to cathode. When you charge, the lithium moves from the cathode to anode, right? So that means the movement of lithium will be enhanced with the temperature, so that may reduce the that may enhance the current that you get from the battery at a given overpotential. So in place of lithium, is it possible to use other alkali metals? Yes, certainly there are sodium batteries and potassium batteries, magnesium batteries are known in the literature. So nickel metal hydride battery and rechargeable battery, there is no difference because nickel metal hydride battery also is a rechargeable type battery. Okay. Is the efficiency of the battery depends on the activation energy? Yes, it is depends on the activation energy. If more is the activation energy, more will be the voltage loss. That means the amount of voltage which is while discharging the battery will reduce. Okay. So power of the battery is current that delivers multiplied by the voltage at which it delivers the power. That's the power. So if the activation energy is higher, means the voltage will be lower. Okay. For the same current, we have a less power now. So we need to look for a way by which you can reduce the activation energy so that the power of the battery is maximized. So why does the efficiency of a battery decreases on repeated use? There are several kind of efficiency when it comes to battery. So battery can have energy efficiency. When I say energy efficiency, that means how much energy that you supply during charging, how much energy comes out during discharging. That is energy efficiency. Sometimes you can also call Coulombic efficiency. Coulombic efficiency. Coulombic efficiency means how much charge applied during charging and charge recovered during discharge. That is charge efficiency, and you may have voltage efficiency. Voltage efficiency is just a product of energy efficiency is a product of voltage efficiency and Coulombic efficiency. If you see voltage efficiency, the voltage of charging at a particular current, okay, at the same current, what is the voltage during discharge. So there are several types of efficiencies are there. Sometimes you will have 100% Coulomb efficiency, but voltage efficiency may go down because the battery may be discharging at lesser and lesser voltage with the number of cycles. So in that case, Coulombic efficiency may be constant, but voltage efficiency may go down. But I told you the energy efficiency is the product of Coulombic efficiency and the voltage efficiency. If Coulombic efficiency go down or voltage efficiency go down, it's going to affect the energy efficiency of the battery. So we need to make sure the energy efficiency of the battery remains constant. So for that, the battery has to have a good Coulombic and voltage efficiency. Is it possible to use any fuel in fuel cells? In principle, yes, but there are some practical constraints. For example, suppose I use platinum to oxidize hydrogen gas. So it will produce 2H plus. Platinum will be is a catalyst, so it will be there. 2 electron. Suppose in place of hydrogen, if I use say methanol, what will happen is methanol also oxidizes plus 4 electron, but there will be a CO, carbon monoxide, which is coming from the methanol, may be irreversibly adsorbed on the platinum surface. That means you need more energy to dissolve this carbon monoxide from the platinum surface. This way, as the fuel cell operates, more and more platinum catalysts will be poisoned by this carbon monoxide, and at one point the fuel cell will stop working. So in principle, yes, any fuel can be used, but we may also have to change the catalyst in order to solve problems something like this. In case of methanol fuel cell, instead of platinum, people use platinum ruthenium because the ruthenium is expected to scavenge the carbon monoxide adsorbed on the platinum, thereby freeing the platinum sites for further reaction. So you can use fuel, also you may have to change the catalyst that you are using for that fuel. So lithium TiS2 batteries, this is like another layered structure like graphite. So lithium is intercalated between the TiS2 layers in this case. I think I answered all your questions, so I will stop my lecture at this point. right? Thank you for listening.